Hello and welcome to our first episode in this new webinar series, Silicon Photonics Explained. I'm Ramzi Salim from Cornerstone. We're really excited today to have you with us as we're kicking off this new series. It's going to be a lot of different talks over the next few months, super cool talks, and in fact there'll be a talk every month for the next 4 months, 4 episodes. So we'll be talking about a range of different key silicon photonics technologies. So in May, for example, there'll be how silicon photonics circuits are made. You can find out about that and about how the fabrication process works, insights into it as well. Whereas in April, there'll be a mid-IR silicon photonics talk. And that where you'll find out there about silicon photonics and how it's impacting the world from medical applications into space. In March, in just a few weeks from now, in fact, the 20th of March, if you want to put that down in your diaries, there'll be a talk on silicon nitride and how it's shaping the world we live in, from quantum level all the way to our everyday lives in terms of telecoms and datacomms. Today we have a very special treat for you. As seen in Nature Photonics, you'll be hearing from 2 of the scientists behind not only the world's fastest integrated traveling wave mass ender modulator in silicon photonics, but also the world's lowest power consumption in that category. But before we jump into that, just give you a quick show and tell of how to access these technologies in Cornerstone. So the first thing you'd want to do is the very kind of top thing is just go straight to our website. And on our website, there's a cornerstone.suttonfab.co.uk. If you go over to our design rules, where you can click on design rules, find out what are the live calls, look at the PDKs, what are the different designs that are available. Everything is open source. You can check out all the details. There's nothing hidden. You can check everything out, all the design rules, all the process techniques, and select the one that you want to work with. Once you have an idea of what it is you're wanting to go with, you want to go to the sign up form. This is essentially to book your slot on the MPW run. So to avoid disappointment, you're able to make sure that you've got space on it while you work on your design. And we would encourage you to let us know as soon as possible. The latest typically is 4 weeks before the mask submission. And how can you find out these deadlines? Well, right here, if you just go over to our MPW schedule, you get a table of all the different runs we have during the year, all the multi-project wafer runs that we have during the year. In fact, for example, you can see here at the moment, there is a 314 nanometer SOI run that is currently open. And the deadline for that, for the mask submission, is 27th of March. So for example, here we're saying the 314 nanometer SOIs, there are design rules that are published already. You can access them, but you can also then let us know through a sign up form. That will be this week. For example, people will have already told us this week that they're signing up, or the latest will be people telling us later this week. And then the final submission for the mask will be the end of March. But if you have any questions about that, you can just go to our email straight away, cornerstone@sutton.ac.uk, and that way you can get in touch with us directly and we can guide you and help you with that. And kind of on the etiquette of webinars, and in fact, maybe we've heard a little bit of sound already here. So number one is that this webinar is being recorded. There will be a Q&A session after the 2 talks. So when the 2 talks are completed, we'll have a Q&A session. There's a Q&A function that people can use to post their questions throughout the talk, and then we'll collate them and ask them at the end. But also we'd encourage people in that Q&A session to open the cameras, talk on the mic, and just kind of ask their questions as well directly. That's great. But in the meantime, I'll ask if we can just make sure our mics are muted, just so that it can not affect everybody else. And but without further ado, allow me to introduce you to our fantastic speakers today. There's Professor Dave Thomson, who will be giving an overview on the high-speed active components, and Dr. Weiwei Zhang, who will tell us all about customized high-speed silicon photonics. Over to you, Dave.
Okay, thank you for the introduction, Ramsey. I'll just share my screen. Okay, hopefully you can see that.
Yep.
Okay, great. So as Ramsey mentioned, I'm going to be talking about high-speed active devices, and mine's going to be related to those that you can access in the MPW runs in Cornerstone. So particularly that active run, you may have noticed from the schedule, there's one coming up in a few months. So that's something that you can access through Cornerstone. So I'm going to start by talking about active photonic devices and silicon photonics in general. And this relates again to the devices that you can make using that MPW run in Cornerstone. And then I'm going to give some examples of some of the active device research that's enabled us to do here in Southampton. So some of our research highlights from the last couple of years. So as we know, silicon photonics is a very attractive technology, and this comes a lot from the fact that we have this CMOS compatibility. And what that enables you to do is to fabricate your photonic circuits in CMOS-like facilities and in a CMOS manner, so in high volumes and with high yield, and that can lead to low cost. And what it also does is it allows a direct integration with electronics. So you can have photonics and electronics, if you want, in the same silicon layer. And that can lead to benefits in terms of performance, but also give you some added functionality. Another advantage of silicon photonics, of course, is the high index contrast between the silicon and the cladding layers. And this can allow you to produce very compact devices. So you can end up with a very densely populated chip that you can fabricate very cheaply. So you can have a lot of functionality at low cost. One of the challenges from silicon photonics, going back to the early days, was the fact that there's no strong electro-optic effect for modulation. For example, like the Pockels effect in lithium niobate. So we've had to find other ways of producing optical modulation in silicon. So one way you can do that is to obviously bring other materials onto your silicon photonic waveguide platform, for example, thin film lithium niobate. And there's been a lot of research in that area in recent years, and also lots of other materials as well. The main problem that introduces, though, is that you compromise that CMOS compatibility, and it complicates how you do the fabrication, and inevitably that may cause an increase in your production costs. So the alternative way you can use is the plasma dispersion effect, and this has been by far the most popular method for modulation in silicon photonics over the last 20 years and more. So the plasma dispersion effect is where changes in electron and hole densities in your silicon waveguide can give you changes in refractive index, which enables you to get phase modulation. And we can use diode-like electrical structures around the waveguide to enable these changes in electron and hole concentration, so that we can have electrical control over the properties of the propagating light. So examples, or well, the three methods that have been used to implement these electrical structures in silicon photonics are shown on this slide. So on the left-hand side, we have the PIN carrier injection structure. And going back to the early years of silicon photonics, this is really the way it was done in large waveguides. And it was only really in the early 2000s that we started looking at these other methods. It's actually, so the way these devices work, it's a PIN diode. So we're looking at the cross section of the waveguide here. and we have p-ion diode, so n-type doping on one side, p-type on the other side for the contacts, and an intrinsic region where your waveguide's formed. And when you forward bias this device, you inject electrons in holes into the waveguide to provide the modulation. Now, these devices are very efficient, but they're also very slow, so limited to speeds of around about a gigahertz. So not really sufficient for the kind of data modulation speeds that we're seeing these days. So that sort of motivated other ways of electrically controlling the carrier density. The one in the middle here has been by far the most popular type of modulator in silicon photonics. It's the one we offer as our sort of core process in Cornerstone, and it's the one you'll find in a lot of other foundries and sort of products around the world. And this is where you introduce a PN junction in the waveguide, and when you reverse bias it, you deplete carriers, and again, this gives you your modulation. These devices can be very fast, so you'll see some results I'm showing later, 100 gigabit per second, but they're relatively inefficient, so device lengths need to be on the order of millimeters. So the third type of structure is the carrier accumulation structure. Here's where you actually have a thin insulating layer in the middle of the waveguide, so that when you forward bias, you accumulate carriers either side of that thin insulating layer, a bit like when you charge a capacitor in electronics. And those accumulated carriers change the refractive index locally to the barrier, and again, provide phase modulation. These devices are both efficient and fast, but the fabrication is a bit more complicated because you now need to introduce this thin barrier in the waveguide and maintain good quality silicon either side to enable you to make a good performing device. So I'm going to be talking a bit more about the depletion device because that's the standard device that we offer in Cornerstone. My colleague will go into a bit more on the accumulation device. That's another structure that we can produce in our clean room here at Southampton. So as I mentioned, the carrier depletion modulator, you have a PN junction in the waveguide, and at 0 volts, you have a depletion region, thin depletion region between the P and N type silicon sections. When you reverse bias, you sweep those carriers out, extend the width of the depletion region, and it's in that extended depletion region you get the change in refractive index. So we can make this type of device using typical electronic type processes, hence why it's a CMOS compatible modulation approach. So these are the process steps we use in the Cornerstone MPW active process. You can see these in the design rules when they're released for this process. I'll quickly summarize them now. So we have first a grating coupler lithography and etch. So this is a shallow 70 nanometer etch into the 220 nanometer SOI silicon layer. And this enables you to form grating couplers to couple light in and out of your silicon photonic circuit. We then define a region where our modulator is going to be and do a background p-type implantation. We then, in the third step, add a silicon dioxide hard mask. And then in the fourth step, use lithography and silicon dioxide etching to define our waveguide pattern in that hard mask. In the fifth step, we use the hard mask to define a silicon etch where we form the rib waveguides into the silicon layer. And then in the sixth step, because we want to provide both strip waveguides and rib waveguides in the same chip or circuit, we have another step where we have resist protecting the rib waveguides, and we have a continuation etch down to the buried oxide layer to form strip waveguides. We then, in the next half of the process, go through three more ion implantation steps to form the light N-type doping, and then the high P and N-type regions. Note that in step 7, we have a self-aligned process to define where this N-type implant goes. So we use an angled implant that is blocked by either the resist layer or the hard mask, and that enables us to define precisely where this junction is within the waveguide every time. And we repeat that angled implant at 60-degree rotations around the wafer to ensure no matter what orientation your waveguide is on the chip, you can configure a modulator that will operate uniformly. So after the implantation steps, we then need to electrically activate the dopants. So we do that by rapid thermal annealing. So we basically heat the wafer up to around about 1000 degrees for a few seconds. And then after that, we can deposit our silicon dioxide top cladding. And then in step 11, we define the positions of contacts down to our doped regions, and we etch those through the top cladding layer. And then we go through metal deposition, lithography, and etching to define our electrodes. And this is what a typical device looks like that you'll get out of our process. So this is a Mach-Zehnder interferometer modulator with phase modulators, carrier depletion phase modulators incorporated in the 2 arms. So you can see an SEM image of the grating coupler, and then a cross-sectional SEM image on the right-hand side showing the modulator region, where we have our rib waveguide and then metal contacts to the 2 sides. So what can be made in the MPW process? Well, it's really focused towards making these PN carrier depletion modulators, as shown on the left-hand side now. But by blocking out the low-doped implants, we can also make PIN carrier injection modulators, or by having P-type contacts on both sides and background P-type doping in the waveguide, we can also do doped thermo-optic modulators. And I'm sure the inventive among you can also think of other clever structures and configurations you can do within the MPW design rules. So what is the device performance? So that's a very common question we get at Cornerstone, and then we'll probably answer with a very annoying answer, it depends. So it's very difficult because there are a lot of trade-offs. So it really depends what you want to get for your overall performance sort of range. So do you want a fast device? Do you want a low loss device? Do you want an efficient device? So for example, if you make your phase modulator very long, you'll have a longer interactional length with the modulation region, and therefore you can get a larger extinction ratio for a given drive voltage. But you'll also have a higher propagation loss, so a higher device loss overall. And your device will also operate at lower speed due to RF losses along the electrodes. Another example, if you move your doped regions closer to the waveguide, you can make the device go faster, but again, that will result in higher loss. So there's a lot of trade-offs you can play off with in the design that can enable you to reach different performance windows as you desire for your specific application. And I think my take-home message from this slide would be that we have the expertise here, if you're not able to guide you to get the performance you need. So if you need a certain performance, please do get in touch and we can help you with that. Having said that, we do publish a sort of performance certification or a sign-off that we go through here, which is a baseline performance that we achieve on all of our runs that we test before we send the chips out. In reality, we hope to achieve better than this, but this is sort of the baseline we publish. And you'll find this again in the design rules when they go out. As an example, performance from our standard MPW modulator, you can see from a 2 mm long Mach-Zehnder modulator, we have a loss of around about 3.4 dBs. We can achieve a nice extinction ratio, getting on for 40 dB typically. We have a phase modulator efficiency around about 2 volts centimeter. And this is an example diagram at 30 gigabit per second, but actually we can go sort of much faster than that, even from the standard devices we find. Okay, so that's the standard MPW modulator. So what can we do with that? So the first sort of obvious application is high-speed transceivers for data centers. So some of our research, we've been working on these high-speed integrated data transmitters. And what we've been doing in that is integrating electronics and photonics. But we're not just talking about integration at the physical level where we're flip chip bonding these CMOS driver chips onto the photonic chip. We're also integrating at the design level. So we're taking into account the photonics in the electronic design, and we're able to overcome some of the limitations and really optimize the overall performance of the integrated photonic electronic module. So as I said, we design the CMOS chips and we flip chip bond them onto our silicon photonic circuits that we fabricate in Cornerstone. The CMOS chips are fabricated at TSMC, but we do all the design of those in-house here. And you can see the schematic of the integration process on the left here. And then on the right-hand side is a final microscope image showing 2 driver chips integrated on a 2-segment Mach-Zehnder modulator. So this specific example here is for producing PAM4 modulation. So we have 2 data inputs for the most significant bit and the least significant bit, and they combine to create a 4-level modulation format. But we've also done on-off key inversions where we have a single segment in each arm of the Mach-Zehnder interferometer. There's a lot of data to take in on this slide, so I'd just like to highlight that with no signal shaping, no pre-emphasis, we're able to achieve bit error rates down to 9e to the -4 at a speed of 112 gigabit per second on-off keying with an electrical energy below a picojoule per bit. And if you're interested in the details of this work, you can find them in this paper shown at the bottom here, which was published towards the end of last year in Nature Electronics. We also have the PAM4 results, where we were able to push up to 224 gigabit per second in that PAM4 format. Again, you'll find all the details of this work in that Nature Electronics paper. So the other thing I wanted to highlight that we've used our MPW run for is to incorporate a chirp generation module into the LiDAR system. So we've been working closely with a company called Point Cloud, who are looking at making LiDAR systems using silicon photonic chips. So if you're not aware what LiDAR is, it's a bit like radar for detecting objects in a certain area of space. But it uses light instead of radio waves, so it can be a lot more accurate. And typical applications are things like self-driving cars. So the systems they're working on at Point Cloud are what are known as FMCW, so frequency modulated continuous wave LiDAR systems. And the way they work is you take continuous wave input light and you modulate it with a chirp signal. So what that means is you modulate it with a sine wave of raising and lowering frequency in this sort of ramp mode as shown in the middle graph on this slide over a period of time. You then take that modulated signal and put it into a beam steering module to enable you to steer the beam and scan the space that you're trying to image. You then get a reflection of that light off the object, and you take a little bit of your output signal as a local oscillator, and you bring those 2 signals, your reflection from your object you're imaging and your local oscillator, and you feed them into a heterodyne receiver, and what you pick up is the beat frequency, or the difference in the frequency between the 2 signals. Now what you'll see in the bottom right signal graph here is that you have a time shift of your received signal in your local oscillator, and that time shift corresponds to the round trip time for the light to reach the object from your LiDAR system and for it to come back, which equates obviously to the distance. And because we have this ramped chirp of the frequency, we can see we have a constant difference in frequency at all points along this graph, and that gives you this constant frequency tone when you mix them together, in this case of around about 400 megahertz, and that enables you to equate this frequency to the distance to your object. And the other thing you can do, if your object is moving, you can have a Doppler shift of that received signal, so the entire red line there will shift up or down, and that will manifest itself as two tone frequencies after you mix them together that you can then use to calculate the velocity of your object. So what have we done using the MPW components within the system? So we produce for LiDAR an electrically packaged IQ modulator and driver. So this is a commercial driver this time, flip bonded onto a PCB. And then we have one of our photonic chips made with the MPW process. And that's gold wire bonded onto the PCB. And we use this, they use this at point cloud to generate that chirp signal to feed into the rest of their system. So the system looks something like this. So our chirp generator goes in here after the laser, then take the light, they split into a transmitter chip, which is for beam steering, and then the other part comes around as the local oscillator into the receiver chip, which has those heterodyne receivers, and also gets the light back from the object you're receiving. And an example of some of the results that they've been able to achieve from a first proof of concept system. So here's some boxes imaged at 54 meters. So this graph on the left-hand side is something called a point cloud, and the different dots in this XYZ space are showing you the position that's equated with their LiDAR system. They've also imaged a wall at 75 meters, and they've shown that with the system they're able to achieve millimeter scale accuracy at a range of 80 meters. And the other really interesting result they managed to achieve with their system is they imaged someone sat in a chair, and what this point cloud is shown on the right hand side here is the different color dots here are velocity. So where you see that the chest region of this person, hopefully you can make out that's someone sat in a chair anyway, but the chest region here is moving. So we're actually able to detect with this system breathing from a distance of 40 meters. So you can imagine there could be lots of interesting and important applications of that. Again, any details, more details on this work you can find in this Nature paper published 2 or 3 years ago. The final thing I wanted to mention before handing over to my colleague is that aside from the fabrication capabilities in offering here, we do have high-speed testing facilities that if you're having trouble with testing, you can get in contact with us and we might be able to help you with that. So our basic capability is chip or board level testing at 1550 nanometers and 1310. We have a bit pattern generator with 4 differential data outputs up to 64 gigabit per second on off keying. We can multiplex them together to get up to 128 gigabit per second, or we can also use a DAC to give you 128 gigabit per second PAM4 signal. We have a DCA for monitoring eye diagrams with an input optical bandwidth up to 70 gigahertz. And recently we've acquired a light wave component analyzer, so we can do electro-optic bandwidth measurements up to 110 gigahertz. So thank you for your attention. I will hand over now to my colleague, Weiwei Zhang.
Okay. Okay, can you hear me? Yeah, you just need to put it in presentation mode.
Okay, good. So in this presentation, I will talk about my 7 years experience working with the
Sorry,
console.
so Weiwei, your slides aren't in presentation mode. Yeah, they're just in normal mode.
But now, is it working now? Emily?
Yeah.
需要放大，太小了现在。
We still see your PowerPoint screen. Maybe it's the second monitor.
I'll show my entire screen will be better. It's good now?
Yep, perfect.
Okay.
Yep.
Yeah. So in this presentation, I will share my around 7 years experience working with the console, and I have customized different high-speed modulators by closely working with the console team. So my presentation will be, firstly, I will show around 4 different modulators that I successfully achieved. And also at the end, I will give some my personal views about research impact and future of our silicon modulators. So when we talk about modulators, especially for the silicon modulators, we always dream how we can reduce the footprints. Typically, for depletion modulators, that David has explained about pin junction type, typically it requires 2 mm long length or above to drive M4 or OK modulator formats due to its limited performance modulation efficiency. Actually, we were able to think about how we can reduce these footprints down to 0.5 mm, or if we use small footprint ring modulators, it can be as small as 5 or 3 micrometers. The second aspect is that how we can continuously increase in the modulation efficiency year by year. I mean, probably similar to the transistors, people scaling the from 28 nanometer node to currently I'm talking about 2 or 3, which is to increase the energy efficiency of electronics. But for our silicon modulators, we also have to think about how we can scale this modulation efficiency for future applications, which means we have to improve the modulation efficiency above 3 watts millimeter. Probably in future will be 1 millimeter that can be achieved by the a lot of foundries, and the users can access to these high efficient modulators. And also we have to think about how to use low drive voltage modulators in order to, in future, that modulators can do a seamless integration with the electronics without the driver amplifiers. And also for silicon photonics, we are also meeting the new applications, for example, quantum applications or free space communications, where the modulator experience a different environment. So we probably have to develop new physics or new designs in order modulators can adapt to different environment rather than data centers. And last, I will show kind of how we can develop silicon-based high-speed detectors, which can be a germanium-based detector alternative, because people has also are trying to address how to increase the yield of germanium detectors. However, silicon-based detectors are similar to, for example, pin junctions, which only depends on the doping. So potentially, silicon-based modulators can eventually reach much higher yield than germanium detectors. And also we can avoid using germanium process. So current silicon modulators, if we check overview of the pin junction, we can see it's all silicon material-based junction, and length typically 2 to 6 millimeters. And we can do MZM modulators, and we can also do remodulators. For MZM-based modulators, the pin junction usually has to be designed with the modulation efficiency around 1.5 watts centimeter or a little bit higher. And for the remodulators, current state-of-the-art that we can drive the modulation efficiency down to around 0.4 watt centimeter, which can provide up to more than 100 gigabaud modulation efficiency speed. And however, for both the two modulators, we have to provide more than 2 watts peak-to-peak driving, which is quite is okay for current technology, may not very good for future development trends. So based on this background, so when I joined Thomson working with the console team, I'm thinking about how we can increase the modulation efficiency. So we propose to do MOSCAP modulators. The difference is that we integrated a very thin insulated oxide between P-type silicon and N-type silicon. Especially one of the P or N-type silicon will be made by the polysilicon materials. So here I show our in-house fabrication. So we start from 8-inch SR wafers. We do thermal oxide growth first as a protection layer for few following steps for CMP polishing. So then we do a trench open and we grow sidewall oxides or the vertical sides. We grow dry oxide. And then we fill in trench with the polysilicon. Then we do CMP. So we can see the initial thermal oxide growth provides a CMP topping layer to protect bottom silicon layers. So then we do weak-edge etching, we do self-aligned doping, as David explained before. So then we'll get MOSCAP active waveguides. So the rest fabrication will be similar to other part of console. We add electrodes, and we can do, then eventually get our MOS modulators. We can see the whole process are quite not that quite complicated. The key process is our first box and second box, where we grow dry oxide on the sidewalls, and we fill the polysilicon and do a polishing. So then the rest of after we get MOS waveguides, actually the wafer itself will be compatible to continue other process, for example, develop other kind of silicon-based components. So which means our process will be compatible with the current foundry process. What we have to do is only add this embedded MOS junctions. So based on the platform, we were able to do MOSCAP modulators based on the SR thickness of 220 nanometer overlay silicon, and also we also made MOSCAP based on the overlay thickness around 500 nanometer SOI. So the modulation efficiency we can achieve is around 0.3 to 0.8 watts centimeter. Now, for example, we made for MOSCAP modulator is a fully integrated driver plus MOSCAP modulator. So we do collaboration with the electronics group to design the 28 nanometer CMOS chip driver, which will take 4 different signals. Each is 25 gigabits per second. Then inside it will mark to 2 channels of 50 gigabits per second differentially. So then we have to drive our MOSCAP modulator. In this first this dash box, we have 2 segments for each arm of MZM modulator. So they will bend it at a U shape to take each differential 50 gigabit per second signal to drive the MOSCAP modulators. So eventually we can get 100 gigabit per second PAM4. So the benefits of our MOSCAP is that you can see even we made our silicon peak as interposer with a lot of electrodes for accessing the DC control and high-speed access, and also a lot of the modulator control part. And for the EIC chip, the size is much larger than our MOSCAP modulator active region area, right? So which means our MOSCAP can provide at least around 10 times the footprint reduction compared with the p-n junction modulators. And we do co-design of electronics and photonics, and eventually we can get very low power consumption. And for the people may ask me what's the insertion loss level of our modulator, I would say at our current version of MOSCAP, we don't get much better insertion loss than p-n junction. I would say the insertion loss level will be same. So the total insertion loss around 6.2 dB, which already include 3 dB quadrature point loss, which means we have around 3.2 dB insertion loss when we're operating PAM4. This is our measured T-deck performance, which means we are at room temperature, we get around 1.5 dB, and when we test up to 90 degree, we get around 2.3. So which overall is good. And considering the power consumption here, EIC power, the estimated power consumption around 2.6 dB, 2.6 picojoule per bit. So the second work we developed for MOSCAP is a MOSCAP remodulator. So for this work, the difference with the p-n junction modulator is because we charge carriers, free carriers, electron holes, or the interface of oxide and silicon. So this concentration of the carriers are much higher than traditional p-n junction modulator, which is around 2 or 3 times order, or 2 or 3 orders higher than traditional p-n junction modulator. So itself will introduce a larger plasma absorption effect. That's why you can see here the coupled emitting ratio of the microring resonances will drift a lot from 12 dB get down to 30 or 40 dB. So in this case, we will see a very large absorption in Hess modulation on the left side of the microring spectrum, and on the right side, because spectrum is broadening when you apply electric field. So the right side will be more kind of suppressed modulation region. So consider nonlinearity or nonlinear dynamics of microring is always to set the best option to set the laser wavelength on the left side of microring, which will provide much stable operation on the right side. So the performance of this microring, we can easily achieve 100 gigabits per second. For the BER, when you put 3 taps FE, we can reach order of 10 to -6 of BER, which is probably one of the best. And also this modulation provides a very good performance, is it can reduce the insertion loss compared with the p-n junction modulators. You can see on this finger B, you can modulate your modulator on the edge of this blue region here, which means that for the one level optical signal, when you calculate signal about OMA, the one level can be above 0.5, right? So which means when you set your wavelengths along this top curve here, the summarized performance in this table is that if you set one level insertion loss around 1.5 dB, you can still get 3.3 dBER when you have 2 watts peak driving voltage. So if you set insertion loss to 3 dB, and you can still get 3 dBER when you only use 1 watts peak driving. So this is an example of the 50 micrometer radius microring performance. However, we even have other microring modulators, which can even further address that. We can use sub-watts peak driving to achieve 3 dBER and with a reasonable insertion loss. So this means we can save in a lot of laser power. The second work I did in CORNERSTONE is about how to develop silicon ring-based detectors. However, we know silicon ring p-n junction-based ring is also a very good modulator. So then we propose a scheme that we design p-n junction, which can be both working as a modulator and also can be working as a efficient modulator detector. So it depends the reverse bias you applied to this pin junction. So you can do co-design of junction, co-design performance of modulator, and co-design performance of detector. So you can use a twin device, two identical device, to one work as a transmitter and one work as a receiver and detector. In this case, we were dreaming it can build an error-free link. So because the microRNA itself is a detector and modulator, so you don't have to worry about the yield of the read devices. And also we can guarantee this each microRNA can cover a O band or C band region. So basically you probably have to develop only two PTK devices, O band and C band microRNA device, to develop let's say it's a around 32 microRNAs for support around 1.6 terabits per second error-free communication links. So this is a kind of dream, but how we can achieve it. So here I show our engineered final performance microRNA modulated detector. For the modulator, we can achieve ER. You can see if we suffer 3 dB or 4 dB insertion loss level, and we consider around 2.5 watts peak to driving, we will get more than 8 dB ER, right? So it's quite larger, on 12 dB. So the ER is large enough. And for the detector itself, we can easily achieve around 0.84 amp per watts, which will be corresponding to optical power around minus 100 microwatts, which is close to the sensitivity of typical detectors. And for the current level, we can see if we switch the photo energy, optical power, from minus 10 dBm to minus 2 or minus 3 dBm, we can see there will be more than 100 microamp and current changing, which means this detector will be enough to support low sensitivity detectors. So this is our characterization of the detector and modulator reference to a lithium beta modulator. Here I would like to note that is when we do the test of detector modulators, we will not use any filters, which means if you use optical filter, you can filter optical noise especially when you're using urban amplifiers. And we also don't use any electric filters inside our scope, because this will significantly reduce in the signal noise, right? In this case, we don't use any filters to show the raw eye performance to determine error-free operation, to show robust communication link can be built without helping of electric signal processing. So at current, we can reach better than 10 to minus 12 BER for detectors at 40 gigabit per second. And for the modulators, we can achieve always error-free more than 56 gigabit per second, as good as lithium beta modulators. However, for detectors, its performance are mostly limited by the SNR, input optical signal SNR. However, the optical SNR is limited by the electric signal. So in our setup, we cannot provide much better electric SNR for 50 gigabit per second, which more or less is below than SNR of 8, which means the source itself will have a limitation of the BER. So here I show the co-design performance of a remodulator and detectors. Why I call here co-design is because when we do co-design, we can enable C-link remodulator provide ER more than 7 dB, right? So we can provide even up to 8 to 10 dB. So when you provide much better, larger ER modulated signal, while you are still keep the received OMA the same, right? In this case, the performance of a detector can reach error-free in our case, which means that the twin device built as an optical link can perform as an error-free link without signal processing. So this is very good for future high-density ring-based communication links for AI potentially. The last device I would like to talk about is the new devices for potentially for quantum optics and free space communications. For quantum optics, some cases we need cryogenic conditions, low temperature operation, and for free space, which suffers radiation from space. Both of these two put challenges to traditional PIN junction modulators, especially in cryogenic conditions. We should rely on carriers. Otherwise, we have to increase more doping to still keep same performance at room temperature. Eventually, we suffer a lot of optical losses, and in free space, the radiation will eventually spoil the PIN junction. So eventually, the modulation efficiency of the PIN junction modulator will degrade a lot after some time. Right. So here we propose, since our first active run in Consto, we developed DC care effects-based modulators, which means the waveguide core itself is an intrinsic silicon, which will not do doping purposely, but there may be some diffuse carriers go to the intrinsic region. In this case, because the doped part is far beyond waveguide core, so we test that actually this kind of waveguide will suffer very small insertion losses than PIN junction modulators. You can believe that this will be a lossless phase shifter. So because it's based on the third order nonlinearity, so we have omega modulation. Omega means alpha frequency, and we also generate 2 omega modulation on this arm. So we characterize in a high speed that both when you apply larger DC voltage, you will get higher modulation and omega. So it's an omega high speed modulation. You can see when the applied voltage is above 6, the modulation will be a linear operation, which will be a quasi Pockels based modulator kind of. And we also characterize the key physical performance at 2 omega. You can say when you do 2 omega modulation, this term is not dependent on any DC voltage, right? So experimentally, we can see no matter how you apply DC bars, it follows a linear fit when you apply the RF frequency, right? So this means a complete demonstration of the high-speed response of our DC cam effect in our modulator. So for the performance, we can do a real modulator when you only apply 4 watts peak driving voltage. We can get nearly error-free 10 gigabit per second modulation diagrams, which means SNR is very close to 15. So to be noted that this modulator is not using any carry effects inside of the waveguide core. So since we here only have to apply the 4 watts peak, so I believe this can be applicable in coming future applications. So this is some of our customized devices. The first one is MOSCAP modulators, MZF version, and remodulation version, which provides much reduced footprints, low voltage driving, and a low optical insertion loss. And we have co-designed junction to support the ring modulators and the ring detectors, and we also developed DC care effects-based modulators to support future quantum and free space communications. So at the last page, I will show just my personal overview about future modulators. I believe that silicon modulators have the potential to achieve 200 gigabaud in future in 5 years, which means we have to do much better EIC and PIC co-design, as Professor Dave Thomson showed earlier. And for high density means we have to achieve around 5 terabits per second per millimeter square density, which we will rely on the tiny modulators. It can be tiny real modulators or tiny MZF-based modulators. It can be both, which means we have to do much efficient modulators beyond 3 watts millimeter efficiency. And for the low power, we already show the trend potential to using MOSFET to develop a sub-watts driving voltage TX, which means drivers may not need it in future. And lastly, for free space communication, which raise a lot of challenging, including quantum optics. So we have to test our different type of modulators, from PN junction to MOSFET or maybe DC-CAR modulators, to compare their performance in different environments. So this will be my end of talk. Thank you.
So what I will do here, I think we've addressed a lot of the questions, and there's super cool kind of more questions that are coming in. We'll try to kind of answer some of them as well on the chat or in the Q&A section. What I wanted to share here briefly as well is what's coming up next, so you have an idea. So on the 20th of March, there'll be a talk on silicon nitride, where we'll be looking at the cornerstone kind of silicon nitride and how it's getting used in applications from quantum to telecom and datacom. So I'd kind of really encourage you to, if you haven't already, make sure you sign up, make sure you add it to your calendars. It's on our website, but also if you're following us on LinkedIn, then you can find it there as well, easy enough to add. But if you're not following us on LinkedIn, you want to correct that and sign up to it and kind of connect with us on LinkedIn to find out what's going on, but also so that we can kind of communicate with you as well. Sometimes these things are through email, which you can do that by sign up to our mailing list, but we can do that through LinkedIn as well, where we can be having different types of conversations as well, and kind of keeping up to date with each other of what's happening from your side and your interest in photonics, but also from ours as well. So I'll stop sharing screen here, and are there kind of, I think maybe here we've kind of covered quite a lot of the questions here. Are there any kind of maybe last comments there from you, Dave and Weiwei, on silicon photonics, from your talks and the questions there? Where do you kind of, so what's next for your research at the moment?
So on one side, we are sort of continuing on this co-design approach to really see how this sort of synergy in electronics and photonics can bring about more enhanced performances and more capability. So we're working a lot on that at the moment, so kind of watch this space. We are also looking at the alternative approach in modulators, so looking at different materials that we can bring in, because ultimately there will be a limit to how far silicon can go. We think we can push it further through these sort of tricks we played, but we think other materials will become more important in the future.
Okay, so integration really, yes. Weiwei, do you have a comment as well?
So I'm more curious. I'm trying to see how to overcome the challenges from the co-packaged optics, which requires the energy efficiency for very high density bandwidth transmitter to be made by silicon photonics, which means for sure driverless will be better, footprint as small as possible, comparable with the electronics, and density should be comparable with the electronics, which means we have to think about any better ways to not using remodulators for that kind of dream.
Yeah. Okay, well, thank you so much, and thank you for the super cool talks, the really interesting talks. In fact, if you're wanting to kind of check out the talks again, they'll be on our YouTube shortly. So later on this week or in the beginning of next week, we'll have them up on YouTube, and we'll put a link LinkedIn post so you can find it there if you aren't already following us on or subscribed on YouTube. But you'll find the episodes there. And we'll look forward to seeing you in the next talk in March in a few weeks. Thank you so much, Weiwei. Thank you so much, Dave. Thank you, folk, and see you again soon.
Thank you.
Thank you.